We said in the last section that we would not calculate the pH of a weak acid or base. But there is one special case where we can at least estimate the pH of a weak acid or a base without a calculator. And that is when we have a 1 molar solution. In order to do these estimates, we need to think about two more P functions, pKa and pKb. Let's see how these work. We'll pick the conjugate pair HF and fluoride ion. If we look on the acid-base chart, here is the entry for that conjugate pair. Since we're going to do this without a calculator, let's for the time being ignore the 7.2 and estimate Ka as 10 to the minus 4. Remember that a P function tells us about the power of 10, with the sign changed, so pKa for HF would be approximately 4. Now, given the actual Ka from the table, the pKa is actually between 3 and 4, but we would need a calculator to get the actual number, so we'll go with this integer. That gives us information about the acid half of the conjugate pair. But what about the base? Remember our relationship between pH and pOH, how they added up to 14? It turns out that pKa and pKb for a conjugate pair also add up to 14, which means that the pKb of fluoride must be approximately 10. And since it is a P function, it tells us that Kb is approximately 10 to the minus 10 power. So again, the table gives us Ka for the acid half of a conjugate pair, from which we can get a pKa, which in turn gives us pKb, from which we can work backwards to get Kb. Got it? Well, actually, if we understand what a P function gives us and the relationship of 14, we can get used to these relationships quickly. We'll come back to this. So, let's estimate the pH of our special case, a 1 molar solution of the weak acid HF. Again, we have the entry from the acid-base chart. What we also need is the balanced equation for HF forming hydronium ion, because we need the concentration of hydronium ion to find the pH. Here is the balanced equation. HF plus water forming fluoride and hydronium. The expression for Ka is this. With fluoride and hydronium appearing in the numerator and HF appearing in the denominator. Remember that it's hydronium that we're trying to find, and the balanced equation tells us the concentration of fluoride and hydronium are equal, and we'll for now call that X. So let's put in some values. Ka is 10 to the minus 4, the numerator is x squared, and the denominator is 1. If we had any other concentration, we would need to get out the calculator. If x squared is 10 to the minus 4, then x equals 10 to the minus 2. Now that we have x, and x is the concentration of hydronium, we can get the pH, which would be 2. You might ask, do we have to do this every single time we want to estimate the pH? The good news is that the answer is no. There is a shortcut. Remember on the previous slide we said that if the Ka for HF is 10 to the minus 4, then pKa is 4? Look at the relationship between the pH and the pKa. Our shortcut is this. The pH of a 1 molar solution of a weak acid equals 1/2 of its pKa. We can go through a similar procedure to find the pH of a 1 molar solution of a weak base. We have to be a little careful since bases form hydroxide, not hydronium. For fluoride, the balanced equation for the reaction with water forms HF and hydroxide. When we are forming hydroxide, it makes sense to first calculate the pOH, which is minus the log of the hydroxide concentration. The equilibrium constant for this balanced equation is the Kb for fluoride. Notice that now in the numerator we have the concentration of hydroxide. Again, the concentrations of the products are equal, and we'll set them equal to X. Remember that the acid-base chart doesn't give the values of Kb for the bases, but we know if the Ka for HF is 10 to the minus 4, then the Kb for fluoride must be 10 to the minus 10. With a 1 molar solution, this equals x squared. X then equals 10 to the minus 5. From that, we know that the pOH is 5. We again look to the pKb for a shortcut. Since Kb is 10 to the minus 10, pKb is 10. Notice that the pOH is half the pKb, which is our shortcut. We haven't actually answered the initial question yet, since we've only found the pOH, but if the pOH equals to 5, then the pH must be 9. That may all seem very complicated, but it's actually not so bad if we understand the relationship of 14, and if we go right to our shortcuts. The acid-base chart gives the Ka for the acid half of the conjugate pair. From the exponent, we can get to the pKa, and half of that number gives the pH of a 1 molar solution. If we know the pKa of the acid half of the conjugate pair, we also know the pKb of the base half. Taking half the pKb of the base gives us the pOH of a 1 molar solution. Be careful, if the question asks for the pH, there's one additional step. A final point is that these shortcuts do not work for amphiprotic species. We can only use them if the acid acts as an acid only, or if the base acts as a base only. We can't get the pH of an amphiprotic material in this way, but we can at least tell if it's acidic or basic, and we'll do that next.